In this lesson, I'd like to discuss one of the more important differentiation tools that we'll be using this semester. And in order to do that, I want to talk about the difference between something we'll call an explicit and an implicit function. So far, most of the functions involving two variables that we've dealt with have been expressed in this explicit form. And all I mean by that is that the y is alone on one side of the equation, all the x's are on the other side. For example, if I give you the equation y equals 3x minus 5, the y is written explicitly in terms of x because the y is on one side of the equation by itself. That's all we mean by explicit. But if I take something like x squared plus y squared equals 9, that is not written as an explicit function. Y is not written explicitly as a function of x. We say that y is an implicit function of x. Whenever y is not on one side by itself, it's mixed in, the x's and y's are mixed in on the same side of the equation. Sometimes, however, finding the derivative of an implicit function is as simple as just solving for y first. For example, if I gave you the equation x times y equals 1 and ask you to compute dy over dx or y prime, that certainly is an implicit function. Y is written implicitly as a function of x. And you could solve it using some of the techniques that we're going to learn here, but it's much easier when it's that simple just to go ahead and solve for y and make it explicit that y is really just 1 over x, or if you want to write it as a negative exponent, which we know is easier to take derivatives of, as x to the minus 1. So even though the original function was written implicitly, if it's really simple to solve for y, that's still probably the best strategy. In order to do that, we've done this before, you just use the power rule and you get minus 1 times 1, which is minus 1, or just minus x to the minus 2, because the power rule says you subtract 1 from the exponent. So minus 1 is minus 2. We've done that. All I'm pointing out here is if you have a really easy way of solving for y, even if the function is written implicitly, you can solve for y and then do what you already know how to do. That doesn't happen most of the time, and we need a way to handle the cases where that is the case. For example, if I gave you something like x squared minus 2y cubed plus 4y equals 2, or x squared plus 2xy minus y cubed equals 5, how would you go about solving those for y? And even if you could, don't you think it would probably be an absolute mess? This is the type of problem that you want to apply what we'll learn in this lesson to solve. But it is solving for dy over dx in either of those two cases is an example of what we're going to call implicit differentiation. To understand how to find that dy over dx or y prime implicitly, you've got to realize that the differentiation is taken with respect to x. If we differentiate terms involving just x, we just differentiate as we usually do, just what we've done in the past. But if we differentiate terms involving y, we have to apply the chain rule or the general power rule, which is just a special case of the chain rule, because we assume that y is defined implicitly as a differentiable function of x, even if it's not explicitly written that way. So we're always thinking in the back of our head, y is a function of x. In other words, y is something that's actually an expression involving x, even if we don't explicitly write out what it is. Now pay close attention to this as we go through these exercises. I want to start off with some really simple mechanics before we go into the problems that we're actually more interested in doing. But I want to do something before I jump into even this. I want to go back and talk about the importance of the chain rule and the general power rule here. We'll be using other rules too, product rule, maybe quotient rule, who knows. But the heart of implicit differentiation is the chain rule, and in practice for a lot of our problems, the special case called the general power rule. Let me remind you, there were several formulations of both the chain rule and the general power rule that you could write down as being each of those rules. And really, you take the one that you're most comfortable with. But I'm going to pick these two. I'm going to say the formulation of the chain rule that I want to present here is the one that says d over dx of f of u, in other words, the derivative of f of u is equal to f prime of u times u prime, where u is some function of x. So the derivative of f of u, where u is a function of x, is the derivative of the outer function, f prime, evaluated at the inner function u, multiplied by the derivative of the inner function u. So the derivative of f of u by the chain rule is f prime of u times u prime. The general power rule, which again is a special case of the chain rule, but we use it so much, it's nice to have it written out explicitly. The derivative of u to n, a power n, is n times u to the n minus 1. In other words, you bring down the exponent, reduce the power by 1, and then you multiply by the derivative of u. Again, n times u to the n minus 1 times the derivative of u prime. So now let's do some really quick examples to sort of get you in the right frame of mind for doing the kind of problems we really want to do. I will say something, most of the problems you'll see use the notation dy over dx, but if you prefer to use y prime, there's nothing wrong with that as long as you know what you're doing and realize that dy over dx and y prime are the same thing. Sometimes it's just a little easier to write y prime than dy over dx. I'm mostly going to stick to dy over dx, although I'll probably sprinkle in some y primes just because that's the way most of your homework appears. But you certainly are free to use y prime if that's easier for you to write. Keep in mind, under the assumption that we're dealing with here, we always have to think of y as a function of x. In other words, y is something that's got x's in it. And that means, in turn, that when you take the derivative of y, you have to say you get y prime or dy over dx. In other words, if y is a function of x, what you get when you take the derivative of y is dy over dx. You haven't written out explicitly what y is, so you can't just jump right in and say y prime or dy over dx is equal to blah. You'll get there eventually, but you can keep in mind that it is in fact the case that y is a function of x, and you can't just say the derivative of y is 1 like you could say the derivative of x is 1. You've got to keep that in mind the entire time. Okay, let's get to these little simple problems I promised you before we get to what we're really interested in, just to get you tuned up. Before I do that, though, I'll also say that I wrote the chain rule and the general power rule using the variable u, but there's nothing special about it, and since we're using y and x so much in this, I'm going to change the u to y. You can do that. It doesn't matter what you call the variable. That just probably makes it a little easier for you to click in your mind that the chain rule and the general power rule apply in these problems. So I just substituted the yn in place of the u. You can use any variable you like, of course, in your formulas. Let's do this little practice I've been promising. Suppose I ask you to find the derivative of 3x squared. Here's what should go on in your mind. In your mind, you should say, okay, there is no y in there. If there's no y in the expression, it's just an ordinary derivative. So the derivative of 3x squared is just 6x by the power rule. No y in there. It's just an ordinary derivative that we've been doing for a while now. Let's do another one. What if I ask you to find the derivative of 2y cubed? Aha, this time there is a y, and you should say, okay, there is a y in this expression, so we must use the general power rule. We're taking the derivative. If it were just 2x cubed, it would just be 6x squared. But because there's a y in there, y is really some function involving x, you've got to use the general power rule. So you do your normal power rule. 3 times 2 is 6. The 3 goes down to a 2. But then because y is a function of x, you have to go back and multiply by y prime or dy over dx, whichever you'd like to write. As long as you're confused about this step, you're going to have trouble all the way through your implicit differentiation work. So it's important that you grasp this early and practice till it's second nature, that whenever you take the derivative of something involving a y, there is going to be a dy over dx or a y prime popping in every time you have to take the derivative of the inside function. Let's do another. What if I ask you to find the derivative of this two-term expression x plus 3y? Well, this is a mixed bag. The first term is just an x. It's an ordinary derivative. But the second term, the 3y, has a y in it, so you have to use the general power rule on that. So the derivative of x is just the ordinary derivative. Derivative of x is 1. The derivative of 3y is just 3 times the derivative of y, which is dy over dx. Or y prime if you'd rather. This is not difficult if you understand the idea that I'm trying to get across, that you always have to treat y as a function of x. One more. What if I ask you to find the derivative of this product, x, y squared? Well, because it's a product, you're going to have to apply the product rule. But within that product rule, one of the factors, the y squared, has a y in it. So when you get to the part of the product rule that requires you to take the derivative of the second term, that's when the general power rule kick in. So as I get started, I recognize it overall as a product rule. So I might think of the x as being u and the y squared as being v. And remember, the product rule says you get u v prime plus v u prime. And of course, u is just x. V prime is the derivative of y squared. Y squared has a y in it, so you have to use the general power rule. So you bring the 2 down, you drop the exponent 2 down to 1, so you just get 2y. But then because y is a function of x, you have to multiply by y prime or dy over dx, whichever you'd rather write. That's half of the product rule. Then you've got your plus sign, and you reverse it. You take v, which is y squared, and multiply it by the derivative of x. X doesn't have any y's in it, so the derivative of x is just your ordinary derivative. The derivative of x is 1. If you want to clean that up a little bit, you'll get 2xy times dy over dx plus y squared. So I want to just play around with some fairly simple cases before we dive into what we really are interested in this lesson. So if you're good with this, that's step 1 to being successful with your implicit differentiation material. I just summarized them all here. That's the 4 problems we just worked. Put them all in one place. You can sort of look at them and go through them in your mind and see how this all works. It's very important that you understand, because as it gets harder, if you're still struggling with the simpler cases, how on earth will you ever handle the more unwieldy ones, for lack of a better term? You've got to understand these basics, or you're not going to be successful in doing the problems that are really the subject of this lesson, which we're going to get to now. Assuming you're good with what we've talked about earlier, you're ready to tackle the problems that are really important in this section, and you'll be able to do them without having to struggle so much. At least that's the idea. I do want to sort of list out the guidelines in general, that you go through these steps as you work these problems. The first step is to take the derivative of both sides of the equation. And remember, you don't have an equation that has y equal to. You've got some equation that has x's and y's mixed together. So the first thing you do when you do an implicit differentiation problem is just take the derivative of both sides with respect to x. Now once you do that, you're going to have one or more terms involving that dy over dx, or y prime if you'd rather write it that way, on one side of the equation, and it may be mixed up with things that don't have dy over dx in it. So what you want to do is isolate all the terms in the equation that have a dy over dx or a y prime in them. Leave those on one side, and any terms that don't have a y prime or a dy over dx in it get moved to the other side. So you want to segregate your dy over dx's from your terms that don't have that. And once you get that done, you'll be able to factor the dy over dx out. I'm saying the left side of the equation because that's the way most people do it. They put the dy over dx term on the left side. And once you get dy over dx isolated as a factor by factoring out of all the terms, then you can solve for it by dividing by whatever is multiplied by the dy over dx. Four-step procedure that you go through on these problems. I will say you use those 4 steps most of the time, but if you get a really simple problem that doesn't require much work, you might find out that you don't have to do all the simplification steps. Most of the time you're going to use all 4 of those steps. I'll also say that it is possible with an implicit differentiation problem, when you end up solving for dy over dx, you could have both x's and y's on the other side of the dy over dx. Typically when you've done derivatives in the past, you had dy over dx on the left and you just had a bunch of x's on the right. But when you're doing implicit differentiation, it's not unusual at all, once you solve for dy over dx, to have both x's and y's in that expression. Okay, I'm ready to finally work a problem which I've tried to build up to. I've taken all this time to try to build up to this. So let's find dy over dx for the equation y cubed plus y squared minus 5y minus x squared equal to minus 4. You just got a multi-term expression, so you can take the derivative term by term. The first step in the process was to differentiate with both sides with respect to x. You're going to take the derivative of the left side and the derivative of the right side. But the left side is just 4 separate terms, so you end up just taking the derivative term by term. So you take the derivative of y cubed, then you take the derivative of y squared, then you take the derivative of minus 5y, and then you take the derivative of minus x squared, and then on the other side you take the derivative of minus 4. Now each of those terms has to be analyzed separately for its derivatives. If you start off and you want to take the derivative of y cubed, you've got to remember just what we were thinking before. That term has a y in it, so it's got to be used. You've got to think about that y as being a function of x, so you're going to use the general power rule. Same thing for this term, it's got a y in it. This one's got a y in it. This one's just ordinary derivative because it doesn't have a y in it, and so is the part on the other side. So when you actually take your derivatives, you're going to get the derivative of y cubed with respect to x as being 3y squared, and then because y is a function of x, you've got to multiply by dy over dx. And then when you take the derivative of y squared, you're going to get 2y. But again, because y is a function of x, you've got to use the general power rule, which says to multiply by the derivative of y with respect to x. Same thing for the third. The derivative of 5y is going to be 5 times dy over dx, because y is a function of x. When you do x squared, though, that doesn't have a y in it, so its derivative is just the ordinary derivative. Derivative of x squared is 2x. And of course, on the right side, the derivative of a constant is always 0. Step by step by step. Okay, what was the next step in the process? The next step was to get everything that had dy over dx in it on generally the left side of the equation, and then move everything else to the right. Well, as you see, the only thing that doesn't have a dy over dx in it is that 2x, that negative 2x. If you move it to the other side, it'll become a positive 2x. And now you notice that every term on the left has a dy over dx in it. That was the goal of that step, is to get all the terms with dy over dx on one side of the equation so that you can do step 3, which is to factor out the dy over dx. since you've got a dy over dx in each term on the left, if you factor it out, you're only left with a trinomial multiplied by dy over dx equal to 2x. Last step then is to solve for dy over dx by dividing both sides by this trinomial. Divide both sides by that trinomial, and you'll end up with dy over dx equals the fraction 2x over the quantity x, 3y squared plus 2y minus 5. And once you've solved for dy over dx, you've done exactly what the question asks you to do, what the problem asks you to do. Step by step by step by step. The big conceptual thing is understanding that when you're taking the derivative of an expression that has a y in it, you've got to treat that y as a function of x, which means you've got to use the chain rule, or in a lot of cases here, it's really the general power rule. So here we want to find the slope of the graph 2x squared minus y squared equal 1 at the point 1, 1 implicitly. Didn't really have to say implicitly because that's the way you're going to have to do that, because the x's and y's are mixed up and it's not easy to solve for y. So even though he said to do it implicitly, it sort of implied that this will be an implicit problem. Well, how do you do that? Similar to what we just did. You want to take that original equation, differentiate with respect to x. You've got two terms on the left and one on the right. So you take the derivative all the way through. The derivative of 2x squared, that's just an ordinary derivative, no y in it, so the derivative would be 4x. The derivative of y squared, there's a y in it, so you've got to use the general power rule. You take 2 times y to the first, which is just 2y, but then you have to multiply by dy over dx because y is a function of x. And then, of course, the derivative of a constant is just 0. So take the original equation, differentiate both sides with respect to x. Then you want to get the terms that have dy over dx on one side by itself. So you could subtract the 4x from both sides, or you could say, well, this term's negative, and you could actually move that to the other side. There's nothing sacred about the dy dx term having to be on the left. You could actually move it to the right. It's totally up to you. I went ahead and just strictly followed the steps. It says to move everything that doesn't have over. But if you wanted to move the negative 2y dy dx to the other side and make it positive and leave the 4x where it was, that's perfectly okay. And finally, you divide out the factor that's multiplied by the dy over dx, and you'll get minus 4x over minus 2y, and of course a minus over a minus is positive, and 2 goes into 4 and leaves a 2, so you end up with 2x over y. The problem says find the slope at a particular point. So although this represents the slope at any general value of x, to find the particular point, we want to know the point, actually I should say x and y. We want to find it at the particular point where x is 1 and y is 1. So all you have to do is plug 1 in for x and 1 in for y, and you'll end up with 2. So the slope at the point 1, minus 1 is 2. Very straightforward if you understand what you're being asked to do.
I'd like to talk a little bit about what implicit differentiation is, how you go about using it, and when you would use it. So let's just start here. Basically, intuitively, informally, I guess I should say, implicit differentiation is a way of finding the derivative dy over dx when the equation specifying the relationship between x and y is not expressed in the form y equal to x. Maybe by contrast, I can illustrate what I mean there. Up until now, before we started talking about implicit differentiation, when you were asked to take the derivative the one thing that all the exercises had in common and of course you can go on and on and on, is that you always had y equal to something. In other words, the equations were always solved for y. And our derivative rules made that assumption as well. But for implicit differentiation, I'll call it ID, situations where implicit differentiation would be appropriate. You might have an equation like x plus 3y squared equals 7, or maybe 4xy plus 4 is equal to 4, x over the square root of y minus 1 is equal to 0. And again, you could go on and on and on. But here's the contrast between the two things. Our old derivative rules up to now have assumed that you're going to have y equal to. Implicit differentiation shows us that we can actually find the derivative without having an explicit equation written in the form of y equal to something where it's a function of x. So even though we're going to think of y as being some function of x, we don't explicitly have to write it that way. So that's sort of what implicit differentiation is in a very simplistic way. Now I want to say something about how do you do it? How do you use implicit differentiation to find the derivative dy over dx? And it's basically a three-step process. Now right now I don't want you to get caught up in all the details, but basically understand the big picture idea. There are three basic steps. First, even though y is not explicitly written as a function of x, like the second column that I was showing you earlier of equations, you do make the assumption that y is some function of x. So if I went back to, say, the equation I wrote earlier, x plus 3y squared equals 7. Even without solving that for y, I'm going to assume that y is some function of x. So that's the first step. Make that assumption. That's very important. Once you make that assumption, and under that assumption, you take the derivative dy over dx of both sides of the equation term by term. So this particular equation, just to continue the example, if I take the derivative of both sides, I'm going to take the derivative of the first term, I'll take the derivative of the second term, and I'll take the derivative of the one term on the other side. Now again, I don't want to get too caught up in the details right now, but that's the process. Now, the derivative of x is just 1. The derivative of 3y squared, by the power rule, if you just think about it that way, is going to be 2 times 3 is 6, and then the y to the second drops down to y to the first. If that were an x, we'd be done. But remember the assumption number one. We're assuming that y is really some function of x. Now we're going to talk about this in more detail later, but for right now just try to keep an eye on the big picture. If y is really some function of x, then we have to come back by the chain rule and take the derivative of the base. And just as a slight aside, it's as if I were taking 2x to the fifth to the third, and if that were the equation that I was trying to take the derivative of, then I would take the 3, bring it down and multiply it by the 1, and that'd give me 3. Then I'd write the base down, and I'd reduce the 3 to a 2, but then the chain rule would kick in, and the chain rule says since that's a function of x, I have to come back and multiply by the derivative of the base, which would be 10x. So that's the same sense that I'm thinking of y back here. Y is some function of x. So when I take 2 times 3 and get 6 and take the 2 down to 1 and get just y to the first, I still have to come back and multiply by the derivative of y, which symbolically is dy over dx. And the derivative of a constant is always 0, so the right hand side would be 0. And the last step in the process is simplify this if you need to, and then solve for dy over dx. In other words, get this dy over dx on one side by itself. And that's easy enough because this problem is pretty simple. I just need to subtract 1 from both sides, and I would get 6y times dy over dx is equal to -1. And then if I divide both sides of that equation by 6y, I would get dy over dx is equal to -1 over 6y. So I don't want you to get bogged down in the details at this point. You'll have plenty more chances to actually look at the details. I want you to focus on the big picture, which is the three-step process. Assume that y is a function of x. Under that assumption, take the derivative of every term on both sides of the equation, and then simplify and solve for dy over dx. That's the big picture. Don't sweat the details at this point. I do want to say this. Although the procedure itself is really simple to understand, and those 3 steps are really not that very difficult to understand, you've always got to be careful. And you've got to remember that whenever you take the derivative of a term, the assumption that y is a function of x means you have to treat the x, or whatever the independent variable is, differently than you treat y. Because y is really a function of x. It's not an independent variable. Let's look at an example just to sort of make that point. Suppose I have 3x plus y is equal to 5. According to our 3-step process, we need to take the derivative of each term. On both sides of the equation. And I'm writing it out formally just sort of for emphasis. When you're doing this yourself, you may not even write down that particular step. But it does emphasize what I'm doing. Okay, the derivative of 3x is 3. The derivative of y with respect to x is what we're calling dy over dx. That's our symbol for it. And the derivative of any constant, in particular 5, is 0. And all we do now is take the 3 to the other side by subtracting 3 from both sides, and you get dy over dx is equal to -3. Simple example, but I think even from such a simple example, there are some lessons to be learned. And I want to emphasize that because that's a very important point here. And I want to do that by just taking some simple derivatives and trying to make my point. If I have just a constant, just say 5 like I had there earlier, its derivative is 0. Derivative of any constant is 0. If I have x, its derivative of course is 1. But if I have y, since y is treated as a function of x, the derivative of y is dy over dx, not 1. If I have something more complex involving just x, say 5x, that derivative would be 5. But if I had 5y, the derivative is going to be 5 times the derivative of y with respect to x. So when you have a constant 0, when you have some term involving just x, it's your ordinary derivative rules, but whenever a y is involved, you're going to have a dy over dx. Suppose I had 3x plus y cubed equal to 5. Looks pretty similar, but it's more complex because the term involving y is more complex. But the procedure begins just the same. You take the derivative term by term. As before, the derivative of 3x is 3. But now y cubed will be 3y squared, but since y is a function of x, you've got to use the chain rule, which says come back and take the derivative of the base, which would be dy over dx. And then, of course, the derivative of 5, as we've said before, is 0. Now, you're still going to subtract a 3 from both sides. You're trying to isolate the dy over dx on one side by itself. In other words, solve for dy over dx. Now, if I divide both sides by 3y squared, I'll have dy over dx on one side by itself. And then you notice, of course, that the 3's will divide out, and you'll end up with dy over dx is equal to minus 1 over y squared. Now, I'm not sure there's really a different lesson to be learned here than the other example, but it is a good point, I guess, at which I can just say this, and that is, whenever you take the derivative of an expression involving y, it will always produce at least 1 dy over dx. When you're taking a term that only has x's in it, or a constant, you're not going to get any dy over dx's. But as soon as you come to a term, or a factor that's part of a term, or a quotient that has a y in it, somewhere in this process you're going to generate at least 1 dy over dx. You just have to remember that. And again, just for an example to look at for later, when I took the derivative of y cubed, I knew when I started I was going to have a dy over dx somewhere in the process. So you think about it and you say, well, the answer is just 3y squared. No, because I have to have a dy over dx somewhere in the answer, and that makes you think, okay, yeah, I remember now, I need to think of y as a function of x, which means the chain rule applies, which means I've got to come back now and take the derivative of the base, which is dy over dx. So be careful, think your way through these, and try to keep in mind these lessons that I've pointed out. Another thing I would say and remind you of is that although implicit differentiation seems like a standalone topic, it's really not. It can involve any of the other rules you've already had for derivatives. I'm not necessarily listing them all of them, but the constant rule, the power rule, the product rule, the quotient rule, the chain rule, the rule for taking derivatives of exponents and logs, all those things are still in your toolbox, and they may be needed when you're doing implicit differentiation. And I'll do a couple of examples to illustrate that. I want to keep it simple, though. My point here is not to work hard, difficult, tricky problems, but to get you to see the big picture. There's more time for actual more difficult problems later. But here's the first example. X times y minus 5 equal to 0. If I want to take the derivative term by term, the first thing I'd notice, I suppose, is that x times y is a product. So that's going to involve me with the product rule. So I've got to take the derivative of that product. Now the product rule, I wrote it down here just to remind you. You take the first factor times the derivative of the second factor plus the second factor times the derivative of the first. So the first factor here is x. So you get x times the derivative of the second factor. Well, the derivative of y is dy over dx because it's a function of x, plus, then you reverse it, you take the second factor, the y, and multiply by the derivative of x, which is 1. So that's the product rule for the first term. Then you've got minus 5. Actually, you've got minus the derivative of 5 when you're writing the differential equation, and that would be 0. And of course, the derivative of 0 is 0. So if you're trying to solve this for dy over dx, those two terms are 0, so all you really have is x times dy over dx is equal to negative y, because that's y times 1 is y, and if I move it to the other side it becomes negative y. And then divide both sides by x, and I get dy over dx is equal to minus y over x. And I've done it. So the point here being, once you're doing implicit, any other derivative rule that you've had might come into play. I would now go and look at some actual problems that might be a little more difficult and see if you can apply what you've learned here. Let's solve some implicit differentiation problems. First of all, we have this one. 7x cubed plus 2y cubed equals 4. And we want to find the derivative of y with respect to x. That means we're thinking of y as a function of x. So the derivative of 7x cubed is 21x squared plus, now the derivative of 2y cubed, remembering that y is a function of x, will involve the chain rule. So you got 3 times 2 is 6y to the second, and then because y is a function of x, the derivative of the base, the derivative of y, is dy over dx. And then of course the derivative of a constant is just 0. Now it's simply a matter of solving for dy over dx. So the first thing I do is subtract 21x squared from both sides. So I end up with 6y squared times dy over dx is equal to negative 21x squared. And finally divide both sides by 6y squared. And I get dy over dx is equal to, and notice there's a 3 as a factor of 21 and a 3 as a factor of 6. So I can divide both top and bottom by 3 and simplify. And I get negative 7x squared divided by 2y squared. And I've found the derivative of y with respect to x. Okay, let's try another one. This time it's a little more complicated. You still take the derivative term by term under the assumption that y is a function of x. So the derivative of 3x squared is going to be 6x plus, now the second term is a product, so you want to think of 3x as one term, as one factor, and y is the other, and use the product rule. The product rule says you take one of the factors and multiply it by the derivative of the second factor. The second factor is y, so its derivative is dy over dx, plus then you reverse it and you take the second factor and you multiply by the derivative of the first factor, where the derivative of 3x is 3. So that's the derivative by the product rule. Then you keep going. The next term, y is a function of x, so you use the chain rule. 2 times 9 is 18. Y to the second drops down to y to the first, and then you come in and take the derivative of the base, so that'd be dy over dx. Moving along, y is a function of x, so the derivative is going to be, the derivative of 7y is 7, but by the chain rule you have to go back in and take the derivative of the base, which would be the derivative of y is dy over dx. Then you've got the derivative of negative 9, or minus the derivative of 9, however you want to look at it. The derivative of 9 is 0. And then on the other side, the derivative of 0 is 0. Now I want to clean this up a little, make it look better. And I also want to collect the terms that have dy over dx together on one side. So I'll write this as 6x plus 3x dy over dx plus y times 3 is more commonly written as 3y plus 18y times dy over dx plus 7 dy over dx. And then those are all 0, so you just got equal to 0. As I said, I want to collect every term that has dy over dx in it on one side. Everything else goes over. So I'm going to subtract the 6x from both sides to move that term over, and subtract the 3y from both sides to move that term over. So what I end up with is 3x times dy over dx plus 18y times dy over dx plus 7 dy over dx, and then the other two things move to the other side, so I get a minus 6x and a minus 3y. Now that I have dy over dx in every term on the left, I can factor it out. So if I factor a dy over dx out on the left, I'm left with a 3x from this term, an 18y from this term, and a 7 from the final term. Now if I divide both sides by this quantity on the left, this 3x plus 18y plus 7, I'll have dy over dx. So dy over dx is minus 6x minus 3y divided by this factor here, which is 3x plus 18y plus 7. So now I've found dy over dx for that problem. Let's keep going. This time I have a product rule on the left. So the product rule says to find the derivative, I take the first factor, which is an x, multiplied by the derivative of the second factor. The second factor is y squared, but y is a function of x, so it'll involve the chain rule. So I get 2y, and the 2 comes down to 1, but then I have to take the derivative of the base, and the derivative of y is dy over dx. That's the first half of the product rule, plus then I reverse it and take the second factor and multiply it by the derivative of the first. Well, the derivative of x is just 1. And then, of course, the derivative of 4 is 0. Now it's a matter of just solving for dy over dx. So I get, just clean this up a little bit, that's 2xy times dy over dx plus y squared equal to 0. I want to slide the only term that doesn't have a dy over dx to the other side, so I'll subtract a y squared from both sides. And that'll give me 2xy dy over dx is equal to negative y squared. And finally, just divide both sides by 2xy, and I'll have dy over dx is equal to minus y squared over 2xy. And the one thing that you need to be careful about here is there's a y here and there's a y in here, so I can divide a y out of the numerator and denominator. So you do need to look to see if there are any simplifications that you can carry out. And so now I've found the derivative of y with respect to x. Okay. This is sort of an application. It says if x squared y squared equals 64, find the equation of the tangent line to this curve at the point 1, 8. In other words, you've got a curve here, and there's a point of tangency at 1, 8, and you want to find the equation of the line. Now remember that you need to write the equation. To write the equation of a line, you need a point, which we have, and the slope, which we don't have. But we can find the slope because the slope is the quantity dy over dx that we've been calculating. So all we need to do, once we realize that, is find the slope. We already have the point using implicit differentiation. So if we go back to this problem, we're going to use the product rule on the left-hand side. So you got the first factor, which is x squared, times the derivative of y squared, assuming y is a function of x. That'd be 2y to the first, but then you've got to come back by the chain rule and take the derivative of y, which is dy over dx. Plus, now you reverse it, you take the y squared and you multiply by the derivative of x squared, which is 2x. And then on the right-hand side, the derivative of a constant is 0. Now it's just a matter of simplifying it and writing this with dy over dx on one side. So what we really have here is 2x squared y times dy over dx plus 2xy squared equal to 0. So I want to leave this where it is and move this term over. So I get 2x squared y times dy over dx equal negative 2x y squared. Then if I divide both sides by that 2x squared y, I get dy over dx is equal to negative 2xy squared over 2x squared y. Now I hope you'll notice that this will simplify quite a bit because the 2's will divide out, leaving with the negative sign up there. This x will go into that x squared, taking the x completely away, and this y will go into that y squared, leaving a y. So up top we're just left with minus y. Down bottom the 2's divided out. This x went into that x squared and left an x, and the y divided into that y squared, so it went completely away. Now that's the derivative of y with respect to x, but we want the derivative, we want the slope at this point right here. So we have to actually take this value of x, which is 1, and this value of y, which is 8, and plug them in here so we'll be able to solve. So let me move over here. So at the point 1 comma 8, where x is 1 and y is 8, dy over dx, and I'll write it this way, at the point 1 comma 8 is going to be negative whatever y is, which would be 8, divided by whatever x is, which is 1. So the slope of the line that we're looking for is just negative 8 over 1, which is negative 8. So now I have the slope of the line and I have the point on the line. Once I have that, I can find the equation of the line in what's called point-slope form. And the point-slope form of a line is y minus y1 equals m times x minus x of 1. This is like the x of 1, y1, and this is the slope. So if I plug those numbers in, I get y minus 8 is equal to m, which is negative 8, times x minus x of 1, which is 1. And we want to simplify that. So you end up with y minus 8 is equal to, if we multiply the parentheses, we get minus 8x, minus a minus is plus 8. And then if we add an 8 to both sides, we end up with y equals minus 8x plus 16. So that is the equation of the line that they're asking us for. It's tangent to this curve at that point. Let's look at one more application problem. It says the demand equation for a certain product is 2p squared plus q squared equals 1200, where p is the price per unit in dollars and q is the number of units demanded. They want us to find dq over dp, in other words, the derivative of the quantity with respect to the price. So the q is like the y and the p is like the x, if you're thinking of dy over dx. So the p is the variable and q is a function of p. So whenever I take the derivative of q, I've got to use the chain rule and think of that as dq over dp. So you got to look at this. The q is like the y and the p is like the x. So looking back at the equation, p is like the x, so the derivative of 2p squared is going to just be 4p, plus the q is like the y, so it's a function of p, so the derivative using the chain rule is 2q, the 2 goes to 1, but then I've got to take the derivative of the inside, which is dq over dp, the derivative of the quantity with respect to the price. And then of course the derivative of 1200 is a constant, the derivative of a constant is always 0. Now I'm going to move the 4p over by subtracting, so I'll get 2q times dq over dp is equal to negative 4p, and then divide both sides by 2q, and I get dq over dp is equal to negative 4p over 2q, and of course there's a 2 inside of that 4 as a factor, so I can divide that out. So I get dq over dp is equal to negative 2p over q. And now I have found what they asked me to find.